All right, so let's say I have in a circuit where collector current, let's say collector current is given as 50 milliamps with a beta DC of, let's say, 150. Usually beta DC will be given it to you in a lot of problems because that's usually come from the manufacturer. So let's say what the problem is asking, what would be the base current? So what is the base current? So that's one problem. Let's say in the next one, IB, which is the base current given as 100 microamps, with beta DC is given as 100. Calculate the emitter current. So anyone got a result for the first one? Yeah. You said 7,500 milliamps. 7.5 amps. Just think about it. If the base current is 7.5 amps, how much collector current given to you? Does base should be higher or collector should be higher? So, however you do the calculation, that was wrong. You probably multiplied these two, correct? You probably, yeah, it's not a multiplication of these two. Remember that the formula is the beta DC you're asking for IB here. So you don't divide or multiply these two. What? No, how much you got? That's correct. So if you do 2, you said E minus 4, right? If you do 2 more, that's negative 6, which is micro. You see what I'm saying? That's what it means. That's what that means. Yeah. So how are you going to rearrange this? So you're saying that 50 milliamps times 150? That's wrong. So what you should do is, when you rearrange the equation for IC, or sorry, IB, so remember that IB is in the denominator. So this IB goes here and bring that beta DC. So the relation is yeah, that's your probably algebra. $333.33 microamps. So the base current should be 333.33 microamps. That's what you will get. Always remember that base current is usually smaller than the collector current. So if you think anything other way around, it's going to be wrong. That's like 09990099, something like that. That's way back, right after you born. Swapping the denominators is easier if you're looking for the denominator. So whatever on the left side will be under the denominator. Whatever on the denominator will be. It's like a cross multiplication. Yeah, you probably learned maybe differently, but this is how you can easily do it. The second one is the base current is 100 micro. The beta DC given as 100. Asking for emitter current. So you definitely need to think a little bit on this one. Because remember, the formula for emitter current is collector current plus the base current. But in this problem, the collector current wasn't given. So when we find collector current from the given information. Yeah. All right, so the result you should get is 10.1 milliamps. So the result you should get is 10.1 milliamps. So even though the problem is asking for emitter current, remember that emitter current is a combination of collector and base. So base current is given as 100 micro, but collector current is unknown. Again, from the same relation where beta DC is IC over IB. So beta DC is given as 100. We are finding IC, IB is given as 100 micro. So all you do is cross multiply. So IC is 100 times 100 micro. So that's 10 milliamps. So collector current would be 10 milliamps. And you use this to find the emitter current. So 10 milli plus 100 micro. So that would be the emitter current. You see that emitter current is always going to be the highest current, which is 10.1 milliamps, whereas a collector current is only 10 milliamps because the base is only 100 microns. The other voltage is from the collector. So you just need to see how we can use these formulas, but you can definitely find the rest of the currents if the beta DC and at least one value of current is known. Same thing with the alpha DC as well. It's collector to the emitter. So you take the collector current and then the emitter current. If you take the ratio, you will get an alpha DC. All right, so that's usually given. Let me show you the data sheet of one of the transistor kind. Down the line in various courses, you will be asked to reference the data sheet to actually find it. 2N3904 is a widely used transistor. We will use in a lot of labs as well. It's an NPN transistor. You can see obviously the symbol for it right here. You see arrow pointing out like that. Visually, the transistor looks like this. In the next lab, you will see how it's going to look like. But there are some maximum ratings we should observe. So you see under maximum ratings, the maximum collector current you can have is 200 milliamps. So anything above that in any application that you're planning to use it may cause a heat developed on the collector side and you can eventually damage the transistor. So that's one collector current reading I want to show you. And the beta DC, as I mentioned, in the data sheets, beta DC referred as HFE value. So 2N3904, for the values they tested, the minimum beta DC is around 40. So maximum it can go 100, 150, 200, depends on how we use it. And look at the VBE. Remember VBE, we need to hit 0.7. So these are the ranges of what the voltage will look like under testing conditions. So, and of course, you see plenty of other values. We will talk about the rest as we go on with the transistors. But that's this under the category of general purpose, not a special transistor for specific application. So yeah, we always look into that continuous current rating, see if that fits for our application. Remember on the multi-sim, we have that lamp example. That lamp is taking like 600 milliamps. So if we use this, we could damage the transistor too. So, all right. Anyway, let's turn our attention to the base perspective. So as you observe, as you know, there are two loops in this circuit, correct? One is from the base perspective. So which is this side of the loop. Two loops, three currents. Loop is a closed path, right? So this slide is only going to be talking about the first loop. You guys remember Kirchhoff voltage law, correct? Sum of the voltages should be equal to the source voltage. So what in this loop you will see, I'm going to redraw this side of the loop purely on this side. So I'm going to ignore the other side. So this side of the loop, what we have here is called as supply name as VBB. That's the base voltage supply. You're going to have RB. So what do you think that is? It's a base resistance, right? That's a resistor symbol, right? So if you have this side of the loop like this, then you're going to have some current is happening on the base, some current happening on the emitter. And finally, the voltage between base and emitter, which is usually referred as VBE. That's what those labels stands for. VBB is for whatever the voltage source on the base. RB is the base resistance, which will cause some base current. VBE is the voltage between base to the emitter, which always going to be, what is it? R is for resistance. So it's only the base resistance. There is no V in there, right? Yeah, then it's a voltage on the base. On the base resistor, yeah. So the VBE value, which is, remember that the base emitter junction has to be forward biased. So the VBE has to be approximately assumed as 0.7 volts, like in the diode forward bias. So if you look at this equation, this is the Kirchhoff voltage law. Total source voltage VBB is equals to whatever the voltage drop on the resistor RB plus whatever the VBE is. So if you rearrange all those equations, this is the final equation that we are intended to follow, which is usual, which should be on your formula sheet as well. So in order to calculate the base current, we take the base supply minus VBE. So how much is VBE? So VBE will be 0.7 divided by whatever the resistance on the base side is. Base to emitter. It's usually indicating the double perspective. It's still VB, is still saying as a base source. There is no explanation why it's called as a two Bs. So that is correct. So VBB is the supply on the base. VBE is the voltage, that's what V for, between base to the emitter. Again, all these subscripts indicating the transistor leads. So RB is just resistance on the base. Of course, IB is the base current. IE is the emitter current. So these are all in relation to the transistor terminals. Remember, even this is the same thing we do in the diodes too. Remember, when you take away 0.7, that's exactly what this is. Remember the half wave rectifier. If you have 5 volts going through the diode, when the diode is forward bias, you take away 0.7, correct? So the result would be like 4.3 volts. So it's the same exact formula on the base loop perspective, where VBE is always going to be that 0.7 for silicon-based transistors. That's the minimum voltage needed to forward bias the junction. So we automatically, theoretically, it's going to be close to 0.7. So to put, yes. That is correct. Yes. So let me give you only, again, this is only that loop one perspective. So let's take an example from that perspective. So let's say we are looking for what is the current flowing through. So this is on the base, correct? So it's the base resistor. So what is the current flowing through the base resistor or current flowing through the base? Subsequently, what is the voltage on the base resistor? So let's say this is from the loop one perspective. These are the values that we are trying to calculate. So the formula for base current is so it's a VBB So it's a 5 is the VBB. Remember that this source is the base source. VBE value is zero point 0.7 over the base resistance is 1K. So if you do the math, this is going to end up with, yep, 4.3 over 1000. So it would be 4.3 milliamps. That's the current flowing through the base, which is same as, you can call it as anything. You can call it as current flowing through the base. You can call it as current flowing through the base resistance, because this whole thing is in series until here. So this one you can also call, this is the base current as well. The base current, yes. So that means I have 4.3 milliamps that is going down towards the base side. So voltage, remember the VBE is also 0.7 between base to the emitter. So what do you think the VRB is? Which is the voltage on the base resistance, meaning that if you test the voltage right here, how much voltage should I read? 4.3, because the source is 5 volts, the VBE is 0.7. So in fact, the numerator of this formula is what is the VRB is, which is 5 minus 0.7, which is the 4.3 volts. So that 0.7 will, 4.3 will be on this resistor. 0.7 will be on the base to emitter. So when you add together, that should be equal to the 5 volts. So we good on this? So if the beta DC given, let's say the beta DC is given as 150, how do we calculate the collector current if the beta DC is given? Let's say the beta DC is given as 150, asking for calculation of the collector current. Which we did the examples in the last couple of slides. So which formula should we use? So what is X? Yeah, remember the formula for BTC is, yeah. So all you do is you take your beta DC, you multiply it with the base current. Remember, I think it's a cross multiplication. So beta DC is 150. You times it by 4.3 milli, which is your base current. Yes, the beta DC is given. So DC current gain, that's what it stands for. DC current gain. That's what beta DC refers to. It's how much It's a ratio between collector to the base, which pretty much implying how much amplification will happen. IC to IB, which is the formula itself. Collector current to the base current. This is one way. Unless if something known on the other side of the loop, we can find the collector current. You see what I mean? The other side of the loop still unknown. So you're saying if I don't know IC and IB, how do I know beta? You need to know at least two in order to find the third. Without that, you can't do it. Then you're going to use the multimeter to test it. That is correct. Beta DC is a calculator value. So if you have a circuit, then you can test for the currents and you can find the beta DC. All right, so you should be able to see these formulas too on it.